So this is my last and final Lab 5 junior venture. The question I'm looking at is momentum conserved in the elastic collision of pool balls? The purpose is not to make a model and compare a model to actual data, but to observe an experiment and subsequently the given principles at work to see if they are being applied, if they're true. How I'm going to do this is I'm going to observe the collision of a cue ball and an 8 ball, use Python to calculate the velocities, momentum, and kinetic energies, and the changes of each of these using a given mass, position, and time data, assuming minimal friction between the two of the balls. And what I got from this was that momentum was not completely conserved, and it was not a completely elastic collision. So I'll go on to explain that in a second. So the physics principles that we're going to use are the momentum principle, Newton's second law, and the elastic collision theory. The elastic collision theory is basically the energy principle. So with momentum, we'll go back up to the top here. The momentum principle says that m1v1 plus m2v2 equals m1v1 plus m2v2. So the momentum initially is going to be equal to the momentum finally. So since the masses for each are going to be the same, we can simplify it to v1 of the cue ball plus v2 of the 8 ball equals v1 of the cue ball plus v2 of the 8 ball. So the elastic collision theory, though, says that for it to be a perfectly elastic collision, the change in kinetic energy of the two balls of the system must be equal to 0. So the change in kinetic energy of the cue ball and the change of kinetic energy of the 8 ball added together have to be equal to 0. So how are these applied to the system? Well, the collision should be perfectly elastic, so their changes of the kinetic energy should be 0. And then the momentum principle is what we're testing. So momentum should be conserved. So the initial momentum should be equal to the final momentum. The assumptions that I'm making in this lab are a negligible effect of drag force in the air and minimal friction from the table. That's a pretty big assumption, but it's an assumption that I'm going to make to start. We're also assuming that the collision of the two balls is going to be at a completely perfect 180-degree angle, so it's going to be straight. And the other assumption that we're making is that the cue ball and the 8 ball are the entire system. So our initial conditions, well, the initial condition when the pool stick contacts the cue ball is 0.208 seconds in my video. The time step was 1/24 because it was 24 frames per second. The initial velocity of the cue ball I calculated to be 0.714. This was done by taking the initial position and taking the change between the first position and the initial position divided by the change in time between those two positions. The 8 ball was initially at rest, so that was 0. The mass of each ball was 160 kilograms, and then the code figured out the rest of the stuff. So this is what the tracker video kind of looked like. The collision was almost perfectly straight, so that was good. You can see the change in positions for each of these over the change in time. We were only looking at the x values because we assumed that it was a 180 degrees collision, so we were assuming that it's only traveling along the x axis. So we were only concerned with the x values and the time data. You can see that there was a little pause right here before it actually connected, or before the cue ball actually connected before the pool stick actually connected the cue ball. So here's some of the code that I was using. We'll start out up here where first I'm going to read into the CSV files of the data that I got from Tracker. Then down to here where I calculate the velocities of each, and you kind of put them in an array so you can iterate through them over there on the left. And then what this does is this iterates through and it calculates the change in velocities for the m1v1 and m2v2, and then this gives you the initial and final momentums, and this calculates the change in each, and then this is the change in momentum for the entire system, which should be equal to 0 if it was, if the momentum principle was being applied. This also down here gives me the kinetic energies of each initially and finally, the change in kinetic energies initially and finally, and then the net change in kinetic energy, which should be 0 if it's a completely elastic collision. So my 3D model, well, this is just basically a 3D representation of what I observed in the lab. So you can see that the momentum was kind of large to start for the cue ball, and then it got extremely smaller because the cue ball kept moving forward. And then the 8 ball started out with a momentum that was almost equally as large as the cue ball and then got successively smaller as the velocity decreased. So here's the graph that I also got from that code. So what the graph shows you is the change in kinetic energy for the 8-ball, the change in kinetic energy for the cue ball, the change in kinetic energy of the system, and the change in momentum of the system. So I know there's a lot going on, but you can kind of see right here, first off, this is where the collision happens. So there's a large increase in the change in kinetic energy for the 8-ball and a large decrease for the cue ball, which is pretty expected. But what this yellow and green, a lot of what's going on here, it shows the change in kinetic energy and the change in momentum. And so it's showing that the change in kinetic energy is directly proportional to the change in momentum. This is because the velocities are changing in a similar manner. So some of the discussion of that is some of the energy was clearly lost to friction from the pool table. It was a pretty crappy table, so there were some worn away spots that could have accounted for some loss in energy and friction and stuff. So this accounts why, when we're looking at the graph, that the change in kinetic energy is going to be negative. So at the end of my code, I also printed out that the change in kinetic energy for the entire system, and it showed that it was negative 11.03. So that much energy is being lost to the system, which I'm assuming to be friction or some other drag force in the air resistance. The model showed exactly what it was supposed to. It was showing the momentum of the system and the change in kinetic energy system. It wasn't really predicting anything, so there wasn't really anything the model could do wrong. It was just showing exactly what I was telling it to based off of the given data and given information. So it wasn't a perfectly elastic collision because the change in kinetic energy between the two pool balls was not zero. There was a net loss of 11.03 joules, which was lost to either friction or drag force in the air. Momentum was also not entirely conserved. It was proportional to loss of the kinetic energy because the velocities were changing. In theory, if it was a perfectly elastic collision, the cue ball should have stopped completely when the two collided, and the 8-ball should have began moving at the same speed that the cue ball contacted it. However, due to friction and a contact that was not complete 180-degree collision, although it was closed, it wasn't completely 180 degrees, not all of the momentum was completely conserved. So my what if question was going to be, what if it was hit harder, softer, would momentum still be conserved? I noticed it when I hit it softer in some of the trials that I did before taking the video, that the cue ball didn't move as much, but the 8-ball also didn't go nearly as far. So friction had a much larger effect when you didn't hit it as hard. But when I hit it a lot harder, it was harder to get it to be a perfectly 180-degree collision. But I also noticed that when I modeled it myself, just kind of on my own, that the effect of friction was significantly smaller, and it made the collision a lot closer to being perfectly elastic, and it also helped show a lot more conservation of momentum, and it was almost completely perfect. So yeah, that's my lab. Thanks.